Welcome to the NCERT Solutions by VYAS Certification. I am Shashir Mittal and I would be presenting the solutions for chemistry for this chapter of class 11th, which is titled as Unit 4 Chemical Bonding and Molecular Structure. This is one of the most fundamental chapters of theoretical chemistry. In case you appreciate this chapter of chemical bonding, gates of two segments, that is organic chemistry and inorganic chemistry, are open towards all the chemistry students. And in case you mess up with this chapter, in case you don't do this properly, you would find complete 2/3 of chemistry, that is organic and inorganic, reasonably difficult. Never mind, I'm here to remove any difficulty which you have. So not only shall we discuss these answers, we will also, by excuse of discussing these questions, we will discuss in detail the concepts which are involved, so that they are not just routine solutions, they also are actually beacons which you can hold to see the path of chemistry, at least with respect to this chapter, and learn the concepts which are involved therein. Are you ready? Let's begin. One more thing. You would find that each question has been discussed separately in independent video and a playlist has been made. Why are we doing it like this? So that you find it easy to locate whichever question. Say for example, you have doubt in question number 11th. So you can directly click on question number 11th without actually having to search and waste your time in browsing through the unnecessary portion. So whichever question you have a doubt in, just click on that and watch. And in case you want to do the entire chapter through our approach, watch all the questions or the solution and discussion to all the questions. You're welcome. There comes the very first question. It says, explain the formation of a chemical bond. So actually, when we talk about a chemical bond, there are pertinent questions like, why is a bond formed? How is a bond formed? And what exactly is involved? So what we shall do, we'll define what is a chemical bond, and we'll also talk about the necessity why atoms actually feel a need to form a chemical bond. Right? There we go. See, how do you define a chemical bond? What is a bond? Bond is actually a force of attraction, right? But then Earth also attracts you. So do you say that you are forming a chemical bond with Earth? Not really. So what is chemical bond? It is the electrostatic force of attraction between two atoms. So we are clarifying. Number one, it is electrostatic in nature. It is not gravitational, it is not a nuclear, weak or strong force, it is purely electrostatic. So what is a chemical bond? A chemical bond is an electrostatic force of attraction. A chemical bond is an electrostatic force of attraction between two or more atoms. Between two or more atoms, such that the magnitude of this attraction amounts to at least 140 to 160 kilojoules per mole. What is the last thing you added? Such that the magnitude of this attraction amounts to at least 140 to 160 kilojoules per mole. Why this? This is also very necessary. This is also very necessary. I hope you understand that. Why? It is necessary because you remember a small time pass experiment which students often do. You take a scale and you rub the scale on your cloth. And especially if you are wearing woolen cloths, much better. You rub that scale on your cloth and then you take small sheets of paper and just hold the scale over those paper. I'll just do it for you. Let's rub a plastic scale, and if we have small pieces of paper, let's expose them to that and observe what happens. I have these pieces of paper. Oh my God, you can see that very clearly they are stuck to plastic scale, they are lifted up. Why? Because they are being attracted by the plastic scale or the electrostatic charge. So is it also electrostatic force of attraction? Yes. So even when a plastic scale is simply rubbed on a cloth and you just hold it over a piece of paper, small pieces of paper, you could see that pieces of paper get attracted. Why? It is again electrostatic force of attraction. Physics people will tell you. Now, if this is electrostatic force of attraction, does that mean that there was a formation of a chemical bond between the plastic scale and the paper particles? No, not really. And that is where the magnitude comes in. At least 140 to 160 kilojoules per mole. If that is the range of attraction, then you can say that there is a chemical bond. right? So this brings us to the precise definition of a chemical bond. So this is the definition. Let me repeat it once again, and you must repeat it with me, because usually a very dilute and approximate definition is used, and this is the accurate one. A chemical bond is an electrostatic force of attraction between two or more atoms such that the magnitude of attraction is at least 140 to 160 kilojoules per mole. This is what a chemical bond is. And this is what is the chemical bond. Now the next part, why is the chemical bond formed? A chemical bond is formed because most of the atoms, if they're alone, they're not very stable. They want to attain better stability by actually coming close to each other or by combining with each other. So how do we put it down exactly in the form of an answer? Let me show it to you. So to put it down clearly, atoms tend to become more stable when they combine with other atoms by making chemical bonds. So what is the reason for making a bond? The most fundamental and simple reason is they want to become more stable, and they attain this stability when they form a bond, and that is why they form a chemical bond. That's it. Question number 2 says, write Lewis dot symbols for atoms of the following elements. Lewis dot symbols mean that you are supposed to write down the atom along with the valence electrons. And what is the number of valence electrons? The number of valence electrons depends upon which group do they belong to. For example, say magnesium. If you belong to S block, then your group number is same as the number of valence electron. Magnesium belongs to group 2 because I have memorized the periodic table, I remember it, so I can say magnesium with 2 dots. Sodium belongs to group 1. So sodium would come with only 1 dot. For P block, now boron, oxygen, nitrogen, bromine, all of them belong to P block. For P block, number of valence electrons is group number, yes, minus 10. So if boron belongs to group 13, oxygen to 16, nitrogen to 15, and bromine to 17. And what is the formula? The formula is group number minus 10 is equal to number of valence electrons. Oh my God, how did you suddenly say 13, 15, 16, 17? How did you write down these names? I have memorized the periodic table. Oh, so are we also supposed to memorize the periodic table? Yes. As students, as chemistry students, you are supposed to remember at least SP and D block very clearly of the periodic table, and the moment I mention an element, you should be able to identify that this belongs to this group and this period. That is a work which you need to do from that chapter on periodic table. Right? If you have not done this till now, go and do it. It is very important, and this will just take you 1 hour, not more than that, but do it. So group number minus 10 is number of valence electrons. So boron, group number is 13, so 13 minus 10 is 3, so 1, 2, and 3. That's it. That's it. What about oxygen? 1, 2, 3, 4, 5, 6. Okay. And nitrogen? 1, 2, 3, 4, 5. And bromine? 1, 2, 3, 4, 5, 6, and 7. These are the Lewis dot symbols for the atoms belonging to various groups, as you can see. The question says, write Lewis symbols for the following atoms and ions. And how do we write down the Lewis symbols? We write down the number of valence electrons as dots, right? So if you say sulfur, now sulfur belongs to group 16. How do I know this? Because I have memorized the periodic table. And there is a formula. And what is that? Number of valence electrons in P block element. This is group number minus 10. Okay. So group number for sulfur is 16. For aluminum is 13, and both of them belong to P block. Okay. So sulfur, 16 minus 10, I have 6 valence electrons. So 1, 2, 3, 4, 5, 6. This is sulfur. What about sulfide ion? -2 charge indicates that there are 2 extra electrons. If there are 2 extra electrons, it already had 1, 2, 3, 4, 5, 6 and 2 more would make it like this. I have drawn the extra electrons in black color. You don't have to change the color. I'm just doing it so that I can point it out to you. Right? This is sulfur and sulfide ion, atom and anion. This is how you deal with this. What about cations? We will have a cation for sure. Just wait and watch. Aluminium has how many valence electrons? Aluminium has 3 valence electrons. So 1, 2, 3. And 3 plus means you have +3 charges. That means in any cation, you remove electrons. You have to take electrons away so that when negative charge is removed, positive charge has been developed. So aluminium cation would be simply Al. That's it. What? I mean, is it barred? It has no electrons? It has no electrons in valence shell. It is just Al. 0 valence electrons simply because it has +3 charge. And that's it. Should I write down the charge? I mean, you don't have to separately. When you're writing down, showing the electrons, this is aluminum atom and this is aluminum cation. No valence electrons, absolutely. Let's take a look at hydrogen also. Hydrogen is an S block. It has only 1 electron. So hydrogen is H dot and hydride ion would be 2 dots. Why? Because it's hydride ion. As simple as that. -1 means 1 extra electron. 1 it already had, 1 more is added. So you get 2. 1 plus 1, 2 valence electron in H minus anion. Take a look at this question which says, draw the Lewis structures for the following molecules and ions. Lovely. And we have H2S, SiCl4, BeF2, carbonate and HCOOH. Let's draw them one by one. Lewis dot structures, when you're drawing H2S for example, there is sulfur in middle and then we have hydrogen and we have hydrogen, yes. Sulfur has 1, 2, 3, 4, 5, 6 valence electrons, right? And hydrogen also has, 1 electron. Sometimes people show it by cross. Since I have the facility to change color, I'm just using a different color, which is also quite okay. And 2 electrons are being shared. Wow. So what do we get? You get H2S like this. Is it the Lewis dot structure? Yes, it is. Otherwise, you could also write it like this. H, S, H. And sulfur has 2 electron pairs which are just lying unshared. So these are also called lone pairs. H2S. What about SiCl4? Now silicon has 1, 2, 3, 4. Silicon has 4 valence electrons. Fine. And what about chlorine? Chlorine has, belonging to group 17. It has actually 17 group number. That means 7 valence electrons. So if you want to draw bonds, akkad, bakkad, Bombay bow, like this, you have 4 bonds. And how do we write down SiCl4? This could be one way to write down SiCl4, yes. Otherwise, you could write it as Si, Cl, Cl, Cl and Cl. Each line indicates that there are 2 electrons on that line. That these 2 electrons, the shared electrons can be replaced by a single line like this. This or this. Lewis dot structures, Lewis dot dash structures as people call them. What about BeF2? Well, BeF2 is, you have Be and you have F and F. Beryllium has only 2 valence electrons and fluorine has, 7. What happens? There is a sharing like this, and you get the loveliest BeF2 in this fashion. You could write it like this, or you could write it like this. This is the Lewis dot structure, this is the dot dash structure. Both the ways it is written, and both are regarded as correct. So we have done H2S, SiCl4 and BeF2. Now let's take a look at carbonate and HCOOH. They are very extraordinary and very interesting. Now the carbonate ion. If you draw carbonate, it should be like this. First you will draw carbon, and you have 3 oxygens, right? Carbon has how many valence electrons? Well, carbon has 1, 2, 3 and 4 valence electrons. What about oxygens? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now it has -2 charge also. If it has -2 charge, that means there are 2 extra electrons which have been added. And what do you think? Which atom actually is going to get those electrons, carbon or oxygen? I mean, whichever is more electronegative would be more likely to receive those electrons. So there are only 2 extra electrons, -2 charge, and there are 3 oxygen atoms. So I suspect that 2 oxygen atoms will actually receive it. So there we are. One more extra electron I have added. Please note that 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. There are 7 electrons each on. So this is O minus, it is O minus. They have -1 charge each. And now they will start making bonds. If they share 1 electron like this, and if they share 2 electrons like this, oh my God, what is this? Well, lovingly you have carbonate ion, and this is C, double bond O, single bond OO, which have minus charge each. Lewis dot structure, Lewis dot dash structure. This is the Lewis structure of carbonate ion. As you proceed, you will notice later on that this is not the structure which is found in nature, but this is the beginning point. In one of the later questions, we will discuss the structure of carbonate ion in greater detail. But then, Lewis dot structure, if you simply write, this is carbonate. Last one, formic acid, HCOOH. Each oxygen has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 electrons like this. And how do we form bonds? That's not very difficult. 1 double bond like this. Right? So these are the electrons sharing structures, or otherwise HCOOH. This is the Lewis dot structure for formic acid, HCOOH. Please remember, in Lewis dot structures, if you eat away the electrons, if you don't write down the lone pairs properly, those structures are wrong. So you have to accurately write down each dot as each electron properly. Write octet rule. Write its significance and its limitations. So take down the octet rule. What does octet rule say? It says that atoms give, take or share electrons. Atoms give, take or share electrons in order to complete an octet of electrons in their outermost orbit. In order to complete an octet of electrons, that means a number 8 of electrons in their outermost orbit. This is the simple statement of octet rule. Fine. What about its significance and limitations? You can do them very easily. Number 1, why is octet rule valuable? Why is it important? Octet rule is very important because it was the first rule which gave us an idea about how atoms combine to form molecules. So the rule which gave us the first method of how to write down molecules with the help of atoms, some guidelines, this was the rule. That is a very major significance, and still Octet Rule is very popular in writing down the structures in organic chemistry. Organic chemistry largely contains carbon, hydrogen, oxygen, nitrogen, such atoms, and for them Octet Rule works very well. This is the significance of Octet Rule. Second point. The third point says the limitations of Octet Rule. Oh my God, Octet Rule has so many limitations. Let me count them one by one. Limitation number 1. Octet Rule is not valid for hydrogen or helium, that is first period elements. For them only duplet is there, only 2 electrons, not 8. Fine. Then for second point, for second period elements, octet may remain incomplete in such cases. Octet may remain incomplete in some cases like BF3, BCl3, BeCl2, BeH2, especially atoms of beryllium and boron. Whenever they form compounds, often they have incomplete octet. And such compounds are called hypovalent. Hypovalent. You know, the ones which have lesser number of electrons than what is required. But yes, are they formed? Yes, they are formed. Compounds like BF3, BeCl2, they are exceptions to Octet Rule. Octet Rule doesn't work with them. So for second period elements, atoms tend to complete an octet, yes, but there are certain molecules, and especially the molecules formed by beryllium and boron, which have incomplete octet. Fine. Third point, third period onwards, Octet Rule may or may not be followed. Oh my God, what does that mean? It means that Octet Rule is totally at the mercy of atoms. Atoms, if they feel like, they follow Octet Rule. If they don't feel like, they don't follow. What is that? It's simple. Like say for example, if you have PCl3, PCl3 follows Octet Rule and PCl5 does not follow Octet Rule. As a matter of fact, phosphorus in PCl5 contains 10 valence electrons, which is, more than 8. Okay, I'll just draw the structures and show you. PCl3 is like this. So 2 plus 2, 4 plus 2, 6 and plus 2, 8. Phosphorus is following the Octet Rule and so does each chlorine atom. What about PCl5? If you have PCl5, Cl, 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 Cl. Chlorines are following the Octet Rule. But if you notice phosphorus, shamelessly it has formed 1, 2, 3, 4, 5 bonds. Each bond contains 2 electrons. That means phosphorus has 10 electrons. Oh my God. In such a case, we say that whenever any atom has more than 8 valence electrons, we say it has an expanded octet. So phosphorus shows an expanded octet. It is also called hypervalent. You can call it hypervalent, you can call it atom having an expanded octet, but yes, that is the case. So third period onwards, Octet Rule may or may not be followed. Sometimes atoms follow it, they just keep 8 valence electrons. Sometimes they may expand the octet and they may include more than 8 valence electrons also. And fourth point, in D and F blocks, Octet Rule is nearly never followed. There is no respect for Octet Rule if you talk about D block elements or F block elements. They don't care absolutely for Octet Rule at all. These are the limitations of Octet Rule. And just as we move ahead, one small observation. Please remember, students, Octet Rule does not work for more than 60 to 70% compounds you will come across. So it is just a generic rule. Had Octet Rule not been so popular in organic chemistry, we might simply have not been mentioning it also. But since it works very well for organic molecules, it is there, just enjoy it. The question says, write the favorable factors for the formation of ionic bond. Right? The favorable factors for the formation of ionic bond. And what are the favorable factors? First of all, please appreciate what is ionic bond. An ionic bond is the electrostatic force of attraction between a positively charged cation and a negatively charged anion. So, if you have ions having opposite charges, the attraction between them is called the ionic bond. right? So first of all, we have to mention that. We have to define what is an ionic bond. And then, what are the conditions which are favorable for formation of ionic bond? Very simple. If you have two elements, out of which one can easily form the cation and the other one can easily form the anion, then you get an ionic bond. That follows directly from the definition itself. So let's write down the same thing. If one of the elements can easily form the cation by losing electrons, okay, can easily form the cation by losing electrons, while the other one can easily form the anion by gaining electrons, then the ionic bond can be formed very easily. If this is simply a short answer, this much is sufficient. But in case it's a bigger answer, you can add two more sentences. What is it which ensures that the atom can easily lose electrons? What is it which ensures that the atom can easily gain electrons? So if you want a longer answer, you can add this portion. Now tell me, which atom can easily lose electrons? The next portion you need to add. So, atoms with low ionization energy. Atoms with low ionization energy. And which are the atoms which have low ionization energy? These are typically metals. Atoms with low ionization energy, that is metals, can easily form cations. Is that the case? Yes, of course. They can easily form the cations. And atoms with high electron affinity. Atoms with high electron affinity can easily gain electrons to form anions. That is non-metals. Right? So if there are atoms with low ionization energy and they are reacting with atoms having high electron affinity, that means metals are reacting with non-metals. Simple. Then they tend to form ionic bonds. So metals with non-metals tend to form ionic bonds. And I think whenever the NCERT asks you a theory question like this, you can take an example also. For example, if sodium, or if sodium is very common, take calcium. If calcium reacts with chlorine, oh wow, what do we get? Well, calcium reacts like, calcium can give away 2 electrons. So calcium had 2 valence electrons and it can form simply calcium cation. And each chlorine atom, how was this? See, Cl, Cl. This is chlorine molecule. And once this receives 2 electrons, that means 1 electron can go to this, 1 electron can go to this. So I will get Cl. 7 electrons were already the personal electrons and 1 more they have received from calcium. The black electrons are from calcium, you can assume, right? So you get chloride ions like this. Wow. So calcium is being surrounded by chloride ions? Yes. They have a cation calcium which is attracting anions which are chloride ions, and this is how you get easily an ionic bond. And this question says, discuss the shape of following molecules using VSEPR model. 5 molecules हैं और हमें उनके shapes discuss करने हैं VSEPR theory के हिसाब से. और क्या क्या है हमारे पास जिंदगी में? Well, हमारे पास है BeCl2, BCl3, SiCl4, ASF5, H2S or phosphine. So let us first take a look at the first member, BeCl2. BeCl2, if you start analyzing the central atom is beryllium and it is linked to 2 Cl atoms, each enjoying 3 lone pairs, which is fine. Now, if you look at the number of electron pairs around the central atom, because in VSEPR theory, what matters is number of electron pairs around the central atom. How many electron pairs do we have? Well, we have 1 and 1, 2. So, steric number, as we call. What is steric number? This is number of sigma bonds plus number of lone pair of electrons. Now, on central atom. This is on central atom. Now, how many sigma bonds are formed by beryllium? 1 plus 1, 2. And how many lone pairs are present on beryllium? 0. So, steric number is 2 plus 0, which is 2. And when the steric number is 2, that means we just need 2 orbitals on beryllium. And well, how would be those orbitals? They must be opposite to each other. If they are just opposite to each other, what happens? You have Be. Now, if Cl atoms repel each other, as per VSEPR theory, they want to go as far apart from each other as possible. And the most apart they can go is they are just opposite. If they are just opposite, this bond angle is 180 degrees. And the structure is linear. Wow, is it linear? Yes, very much. It is linear. This brings us to BCl3, the second in the line. If you try to draw BCl3, well, and you can also try to find out and figure out the steric number of boron in BCl3. Boron is surrounded by 3 Cl atoms. It is connected to 3 Cl atoms by 1 sigma bond each. So, steric number. What is steric number? You might say that I don't know what is steric number, so I am telling you very simply. For central atom, the number of sigma bonds plus number of lone pairs. I have just drawn Lewis dot structure. You can see number of sigma bonds is 1, 2, 3. So, this is 3 and number of lone pairs is 0. So, this is 3. And if the steric number is 3, with each steric number is associated a certain geometry, a certain configuration around the central atom. Like in this case, we will have trigonal planar. So, the geometry would be trigonal planar because Cl atoms would like to go as far apart from each other as possible, and the farthest they can go apart from each other is at an angle of 120 degrees within the same plane. So, this becomes trigonal planar as per VSEPR theory. Very quickly, let's take a look at the remaining ones also systematically. The next one is SiCl4. If I draw the Lewis dot structure of SiCl4, I'll draw it all very systematically before you. Steric number will be equal to 1, 2, 3, 4. 4 sigma bonds plus 0, which is 4. And we have learned the table, we understand and we remember that the geometry associated with this would be tetrahedral. How exactly does it look like? I'll actually show you these animated molecules also. Wow, is it? I mean, first of all, very simple, so we can skip them. But right from 3-dimensional tetrahedral molecules, we will take a look surely. And what about the next one? AsF5. AsF5. If you just consider, the geometry is very interesting. It is trigonal bipyramidal. And why is it trigonal bipyramidal? Why so? Because if you observe, the steric number will be 5 plus 0, which is 5. Oh wow, that is the case. Yes, that is the case. Then we have the lovely H2S and phosphine. Till now, please note, the number of lone pairs on central atom is 0. And when you talk about H2S and phosphine, the story slightly changes because in H2S, you have H, S, H. And in phosphine, you have P, H, H, H. If you watch the steric number, it is 2 plus 2, which is 4, and it is 3 plus 1, which is 4 again. Oh my God, that means the geometry should have been based on a structure which is very similar to tetrahedral. Maybe, whatever. But for sure, one thing is there, it is definitely not linear. And you find that lone pairs also occupy certain space, and they repel and they push around, and thereby, because of all that push, the structure becomes angular. Oh my God, this is angular. Yeah, sometimes people call it angular, sometimes people call it V-shaped. You can call it whatever you like, both are good words. What about phosphine? Phosphine also is very interesting. See, you have 3 bonded pairs and 1 lone pair. If you observe, these are roughly at the corners of a tetrahedron, but since lone pair cannot be seen, so all you can see is phosphorus with H. This is all what is actually observable or is visible. And in that case, the geometry is termed as, yes, it is termed as trigonal pyramidal. It is trigonal pyramidal. Right? Right. Watch out for this very lovely tetrahedral structure of SiCl4. Can you observe the very unique tetrahedral geometry? Can you observe that all the 4 green colored atoms, the Cl atoms, are at same distance from the central atom of silicon? SiCl4, tetrahedral, is a perfectly symmetric structure. Observe this tetrahedral structure very carefully. I mean, the way we have put it here, see, if you join all the corners, this is the tetrahedral structure, and actually you would find that it consists of 4 equilateral triangles. How exactly? It is simple. An equilateral triangle, and from the centroid you take a perpendicular at a 4th point there, and this is the shape of a 3-dimensional tetrahedron. 1 face, 2 face, 3rd face, and the bottom 4th face. This is a tetrahedral structure. Now observe the trigonal bipyramidal structure of PCl5, yeah, ASF5. If you notice, there is a central atom, and to this central atom are attached 5 different fluorine atoms. And I have a few things more to add. Why do you call it trigonal bipyramidal? Because you have central atom, arsenic, then you have F and F and F, like this. And these 3 locations are called equatorial positions. Fine. And what else? And you have 2 more F atoms, and these are called axial. Why exactly? Please note that the angle between equatorial and axial is 90 degrees. So axial equatorial is 90 degrees. On the other hand, if you notice this angle between different equatorial angles, this is 120 degrees. Equatorial is 120. So is this a very symmetric molecule? No, it is not as perfectly symmetric as tetrahedral. Why? Tetrahedral at all bond angles perfectly equal, everything identical. In this case, my dear, there are 2 different locations. Axial bonds are longer and weaker. This is additional information I am giving you. Axial bonds are longer and weaker, while equatorial bonds are slightly shorter and stronger. That is the speciality of this trigonal bipyramidal geometry. You can see that these 2, can you see that this angle is around 120 degrees? So this is equatorial. And this, they are perpendicular. This is axial. And there is one more small equatorial at the back. This is the structure of ASF5. Observe the most unique trigonal bipyramidal structure once again in its 3-dimensional movement. This brings us to H2S, dears. H2S, the simple angular molecule. HSH, and as you can see, this is not a linear molecule. Why? Because there are lone pairs of atoms sitting, lone pairs of electrons, sorry, sitting on sulfur atom, which actually repel and make this molecule non-linear or bent. And lastly, we come to phosphine, PH3, a beautiful trigonal pyramidal molecule, phosphine. This is a lone pair sitting at the top of this location, you can see, which actually pushes the hydrogen down and gives you this trigonal pyramidal structure. This question says, although the geometries of ammonia and water molecules are distorted tetrahedral, bond angle in water is less than that of ammonia. Discuss. And what is the secret? So first, let us draw the structures of ammonia and water. If you draw the Lewis dot structures, you will notice that ammonia has one lone pair of electrons while water has two lone pair of electrons. So one lone pair of electrons in ammonia, two lone pair of electrons in H2O. First of all, we should write down the structure and make this observation. Yes. And we are aware of one fact. What? As per VSEPR theory, the repulsions because of lone pairs are greater than the repulsions because of bonded pairs. What do you mean? We mean that lone pair repulsion is more than lone pair bonded pair, which is more than bonded pair. Which means that these two lone pairs will repel desperately. And if they repel, they want to go away from each other. They will push hydrogen atoms together, thereby reducing the bond angle between HOH. What? Let me say it once again. For example, let me take these two spatula which are there from chemistry lab. And say this is OH and O. This is OHH. Just assume this is water molecule. Now, if I have two lone pairs, now lone pairs are not very distinctly visible. You can't really see electrons like this. But if there are two lone pairs, just imagine if there are two entities which are repelling, which are going away from each other. If they are repelling, they will repel everything, they will repel this also. And if they are repelling and expanding, they will push this angle together closer, thereby making this angle smaller. So greater the lone pair, because of greater repulsion between lone pair and lone pair, greater LP repulsion, and these lone pairs and bonded pairs do not repel as much. So lone pairs, in their bid to go away from each other, they will push the hydrogen atoms together, thereby reducing the HOH bond angle. Right? So what do we write? What do we say? We say that due to greater repulsions between two lone pairs present on oxygen atom in water, they push the hydrogen atoms closer to each other because they are trying to repel. And if they go away from each other, in order to escape that repulsion, H atoms will be pushed closer. And as H atoms are pushed closer, the bond angle becomes lesser in HOH as compared to ammonia, because ammonia contains only one lone pair. And lone pair, bonded pair repulsions. Now lone pair is repelling bonded pairs, and bonded pairs are also repelling each other. But bonded pairs cannot repel as much, and lone pair repels them more. So yes, this lone pair also will reduce H and H bond angle, but not as much as HOH bond angle, because the repulsion between two lone pairs is much more. And that is why. So please tell us in one sentence how do we write it down. You can take down the sentence and write it down. It says first draw this, write down this, and then you can say, since water molecule contains oxygen atom with two lone pairs of electrons, due to greater repulsion between lone pair and lone pair, H atoms on water, on H2O molecule, are pushed together, thereby reducing the HOH bond angle. That's it. That is absolutely sufficient for explaining why water molecule has lesser bond angle as compared to ammonia. A very fundamental question. What does it say? It says, how do you express the bond strength in terms of bond order? Bond strength को bond order के terms में कैसे express करेंगे? Can we do that? Yes. Higher the bond order, greater is the bond strength. Very simple. Higher is the bond order, greater is the bond strength. Bond order increases, bond strength always increases. For example, you can give an example also. If you have CC bond, C single bond C, C double bond C, C triple bond C, bond strength increases. You can say bond strength increases as bond order increases. Bond order increases and that way bond strength also increases. There's a direct relation. Greater the bond order, higher is the bond strength. Define the bond length. What is bond length? The internuclear distance between two atoms connected by a bond is called the bond length. Please note, you cannot see electrons. There is no machine, even electron microscopes cannot see or observe the location of an electron. But the location of nucleus can be identified, nucleus can be located. And how is exactly a bond formed? A bond is formed between two atoms. So if you have two atoms which are bonded to each other, what is the bond length? You take nucleus of first atom and you take nucleus of the second atom and you measure the distance between two nuclei. And that is called the bond length. The internuclear distance between two atoms connected by a bond is called length of that bond. The question says, explain the important aspects of resonance with reference to carbonate ions. Resonance is a very unique concept in chemistry. What does it say? It means that there are molecules in nature. The concept of resonance involves this idea. There are molecules in nature which, if you want to draw their structures, you would not be able to draw an accurate structure using just a single bond or a double bond or a triple bond. So, whenever the actual structure of a molecule in nature cannot be accurately represented by just using single, double or triple bonds, then the concept of resonance is invoked. What do we do then? In that case, we say that the actual structure can be imagined. Please remember, not written. The actual structure can be imagined as if it is somewhere in between more than two or more than two Lewis dot structures which are called contributing structures. That is confusing. Let me tell you this with reference to carbonate ion. Say for example, we write down the structure of carbonate ion. If you draw a proper Lewis dot structure of carbonate ion, it appears like this. There are two oxygens with -1 charge each. You have carbon and oxygen like this. And in this structure, if you notice, there is a double bond and there are two single bonds. If this is the actual structure of carbonate ion, then when we observe carbonate ion actually in nature, we would find that it should contain two types of carbon-oxygen bonds, one double bond and two single bonds. But does it actually happen? No, it doesn't happen. Actually, what you notice is the real carbonate ion has all three bonds perfectly identical. And more interestingly, these bonds are shorter than single bonds but longer than double bonds. That means these bonds are no longer simply a single bond or a double bond. They are something else only. They are somewhere in between a single and a double bond. Now, how do you rationalize that? How do you generalize that? How do you understand that? We can understand this using the concept of resonance. What do we say? We say that this is one Lewis dot structure of carbonate ion, but this is not sufficient for understanding the real carbonate ion. Okay, so what do? Then we say, we just apply some logic. We say, see, look, there are three oxygen atoms. And there is absolutely no reason why should two oxygen atoms carry the burden of negativity and take minus charge, while the third one is enjoying a double bond and no minus charge. Actually, they should share the responsibility equally, right? So there could be a possibility when this minus charge actually lies with these two or with these two. Something of that kind. What are you doing? Double bond could be here, or double bond could be here, or double bond could be here. 3 different locations of double bond can be identified. In the same fashion, the minus charge, instead of just being fixed on 2 atoms, it could be on these 2, or these 2, or these 2. So actually I could draw not 1, not 2, but 3 structures. All of these 3 are perfectly correct Lewis dot structures. You might feel that, okay, if I just rotate this, I'll get this. Rotation is not the problem. The problem is, if you take 1 or 2 or 3 and assume that rotation is not allowed, the atoms are fixed in the space. If you take 1 or 2 or 3, each of these Lewis structures, do they represent the actual carbonate ion? The answer is no. Why? Because the actual carbonate ion does not contain double and single bonds. It does not contain 2 different types of bonds. All the 3 bonds, carbon-oxygen bonds in carbonate, are experimentally observed to be identical, same. And each of these structures says that there is a double bond, there is a single bond, fine. So each of these structures is screaming that there are 2 different types of bonds. That means each of these structures is wrong, first of all. Okay, then what is the concept of resonance? The concept of resonance says that you draw all possible structures and you assume that these structures are canonical structures, or they're also called contributing structures, or they are also called resonating structures. Oh wow, now we understood. The molecule is jumping between 2 or 3 structures. The molecule is not a monkey which is jumping, not a frog either. No. Neither 1 nor 2 nor 3. 1 or 2 or 3 never actually exist. Please remember, they never actually exist. Not even for a microsecond. Then, why you write them? We write them because on pen and paper, this is the human limitation, not the limitation of nature. We imagined the bonds to be just single bond, double bond, or triple bond. So if you want to clearly write down the structures in terms of single, double, or triple, this is the maximum you can do. And the actual structure is neither 1 nor 2 nor 3. It is somewhere in between these 3 structures. What? Yes, it is somewhere in between these 3 structures. And that is the actual resonant structure of carbonate ion. That carbonate ion structure is always present. It is not jumping between any 1, 2 or 3 structures. That is a permanent prevalent structure of carbonate ion which exists from beginning to the end forever. What is that? That structure sometimes is denoted like this. You draw dotted lines which shows that pi bond is not just between this or this or this. Actually, the pi bond is spread over all these. You can say that now you can write down carbonate. Why not write it like this? There is still a problem. We have not quantified how many pi bonds are there, how many lone pairs are there, what is the charge on each atom. These details are missing from this style of writing. So this style is not regarded with great respect. It is just used for imagining that pi bond is not fixed between 1 carbon and 1 oxygen. It is a delocalized pi bond. This is the way we call it. It is a delocalized pi bond. The pi bond is spread out over this zone entirely. So this is the zone on which pi bond or pi electron cloud is spread, and there is a partial pi bond. You could say that because it is between 3 atoms, 1/3 pi bond here, 1/3 pi bond here, 1/3 pi bond is here, and this is how we imagine the structure of carbonate ion. So there is a 1 sigma bond. Yes, so 1 sigma is always there. Please note, in each of these structures, 1 sigma bond is always there. But what is delocalized, what is actually variable, is a pi bond. So bond order of 1 can be attributed to each of these structures, each of these bonds. But an extra pi bond is not fully here, not fully here, not fully here. So we just say that 1/3 pi bond is here, 1/3 is here, 1/3 is here. So 1 plus 1/3, 4/3. We say that bond order of CO bond in carbonate is 4/3. That means, or 1.33. 1 sigma and 0.33 pi bonds. That is the way it is. This is the structure of carbonate ion, and this is how we interpret resonance also with the example of carbonate ion. H3PO3 can be represented by structures 1 and 2 shown below. Fine. Can these two structures be taken as canonical forms of the resonance hybrid representing H3PO3? If not, give reasons. The first condition of resonating structures is that the connectivity of atoms must be identical in each of these structures. What does that mean? It means that whichever way in which the atoms, or whichever sequence in which the atoms are connected in one structure, the same should be the sequence in the other one. Say for example, in this case, phosphorus is connected with one hydrogen, oxygen, oxygen and oxygen like this. There are 4 bonds of phosphorus with OH group, O and H like this. I mean, that's the way they have put it. Fine. What about here? In this case, there's a difference. The phosphorus is bonded to OH and oxygen, and there is a lone pair. Oh my God. There is no hydrogen here. There is no hydrogen here. That is bad. That is actually pretty bad. So is it a good idea? It's a bad idea. Is it a good structure? It is a bad structure. So, are they canonical forms? They definitely cannot be canonical forms. I think a hydrogen is missing here, so I'll just write the hydrogen here. Doesn't matter. See, in structure 1, H atom is directly connected to phosphorus. In structure 2, H atoms are connected only to O atoms. Since connectivity of hydrogen atoms is different, and it was expected to be identical in case of canonical structures, it is not so in this case, and hence they are not the canonical structures. How shall we write the answer in one sentence? Let me dictate that. It says, since the connectivity of atoms is not identical in structures 1 and 2, and you can point out also in brackets, H atom in structure 1 is directly connected to phosphorus atom, while that is not the case in structure 2. Bracket closes, full stop. Hence, they are not canonical structures. That's it. The question says, write down the resonance structures for SO3, NO2 and NO3 minus. Let's take a look. If we have SO3, actually SO3 would go very lovingly like this, and it would not have any significant resonating structures simply because SO3 is the way it is. The most stable structure is this, and the other structures would not be close to stability as comes to this one. If you have NO3 minus and NO2, it is very interesting. This is an odd electron molecule. This is NO2. And the moment you write down this structure, there is an objection. What? Why minus here and double bond here? So you can say that there is a contributing structure. Like this. So NO2 actually is a resonance hybrid in between these two structures. Nitrogen carries an unpaired electron, and the bond order of NO bond is, it is neither 1 nor 2, it is in between. It is average, it is 1.5. This is the structure of NO2. There's one more. Well, write down NO3 minus. If you have seen NO2, I'm going to modify this and convert this to NO3 minus as well. How? Watch. This is NO3 minus. I'm just putting formal charges there, like this. And double bond can here, and there is one more place on which double bond can go. And what is that? Just at the top, like this. So these are the 3 contributing structures of NO3 minus. Bond order, if you care to find out, will be 4 by 3. Why? Because one sigma bond is always there. Pi bond, it is just like carbonate. So pi bond either here or there or there, it is divided between 3. So 1 by 3 is the contribution of pi bond to each NO bond. So 1 plus 1 by 3, that makes it 4 by 3. Use Lewis symbols to show the transfer of electrons between the following atoms to form cations and anions. Let's take a look. We're getting ionic bonds. Potassium and sulfur. Now potassium is in group 1, it has 1 valence electron, and sulfur is in group 16, it has 6 valence electrons. Sulfur actually, from 6, in order to complete an octet, it would need 2 electrons. On the other hand, I hope you can see that potassium is capable of giving only 1. So is this a good match? If not, who says there is only 1 potassium atom? Take 2 atoms. Oh yeah. So what shall we have? Just imagine it like this. And just for the sake of convenience, let me say color the potassium electrons as black. Now electrons, please remember, have no color as such. I'm just doing this for the sake of your convenience. So sulfur has 6 electrons of its own, yes, and it is going to borrow 2 electrons from potassium. Not borrow, rather complete transfer. So you get sulfide ion. Wow. And you have 2 potassium atoms. You get 2 times potassium atoms. That's it. That's it. Simple, very simple. What about calcium and oxygen? Calcium has 2 valence electrons. Yes. And oxygen has 6. So if calcium loses electrons, yes, it has 2 valence electrons, it will throw away both. So it has +2 charge. What about oxygen? As oxygen gains 2 electrons, it would become -2 like this. The black electrons are the ones which have been acquired from calcium. This is how cations and anions are formed, and this is how an ionic bond is established between calcium and oxygen. What about aluminium and nitrogen? Aluminium has 3 valence electrons, and nitrogen, the stupid one, has, why you call it stupid? I just don't like nitrogen much. 1, 2, 3, 4, 5. I have nothing against it, no racism for nitrogen, but still, just a personal choice, like you like red color, something like that. Now, aluminium will lose all the 3 ions, and please remember, losing 1 electron is easier than losing both 2, and losing 2 is easier than losing all 3, which is much more painful because you're losing 3 electrons. But nonetheless, aluminium manages the sacrifice, and nitrogen 1, 2, 3, 4, 5, and then you get 6, 7, 8. Nitride ion. This is how you get the ionic bond for aluminium nitride. Although both CO2 and H2O are triatomic molecules, okay, the shape of H2O molecule is bent while that of CO2 is linear. Yes, indeed. Explain this on the basis of dipole moment. Actually, see, you cannot see molecules very easily. Even 100 years back, when all these discoveries were going on, this was a very difficult affair. Electron microscopes or spectroscopic methods can now give you some understanding about the location of atoms within a molecule. But please remember, this is not easy. It's a difficult thing. So before people actually could measure and see those molecular structures, was there a method? Yes. And that method was actually the method of dipole moments. And how do we do that? First, let me quickly tell you what is a dipole moment. See, if you have a covalent bond, which is a polar covalent bond. Say for example, if you have a covalent bond between H and O or C and O, different atoms have different electronegativities. What does that mean? It means that they have different tendencies to attract the shared electron cloud or to pull the shared electron cloud towards themselves. For example, oxygen is more electronegative than hydrogen. That means oxygen has a tendency to pull the shared electron cloud more towards itself. If that is the case, hydrogen will develop a slightly positive charge and oxygen will develop a slightly negative charge. This is what we call as an electrical dipole. What is it? Take it easy. It is just a name. Two charges which are placed close to each other but separated by distance. Opposite charges, positive charge and a negative charge of same magnitude separated by small distance. This is called an electrical dipole. And how strongly this electrical dipole attracts or repels another electrical dipole, that strength of repulsion or attraction is measured by a quantity which is called dipole moment. Oh wow! How do we calculate this dipole moment? There's a formula for that. Dipole moment mu is Q into D. D is the distance between these two nuclei and Q is the charge. Like you have Q plus and if you have Q minus, then you just multiply charge by distance and you get this funny thing called as dipole moment, and this dipole moment is a vector quantity. So if you have a polar molecule, yes, the OH and CO bonds are polar, yes, they are polar bonds. In these cases, oxygen atoms acquire minus charge and hydrogen or carbon atoms acquire slightly plus charge. Okay. So if you have, a polar bond like this, the molecule also is expected to be polar. Yes, because if you have polar bonds, then the overall molecule also should be polar. But there's a problem. Carbon dioxide is found to be non-polar. CO2 is experimentally found to be non-polar. What does that mean? It clearly means that atoms of oxygen are arranged in such a way in CO2 that their dipole moments must be able to exactly cancel each other. That means they must be exactly opposite to each other. And if they're opposite to each other, then the structure would be linear. Yes, the structure would be linear. That's how we judge it. That's very simple. Of course, that's very simple. Why should it be difficult at all? The structure of CO2 is linear because if it is not linear, dipole moments exactly will not be able to cancel each other and CO2 would not be non-polar. But CO2 is experimentally observed to be non-polar, which means that dipole moments must cancel each other, which means that CO2 molecule has to be linear. Otherwise, if the oxygen atoms are not exactly opposite to each other, dipole moments will not cancel each other. They will add up partially. And that partial addition actually happens in water molecule. Why? It is observed that water molecule has a net dipole moment. Now imagine if water molecule had been like this, then dipole moments of OH bonds also should have cancelled each other, right? Like this. They should have cancelled exactly opposite. But it is very well known that they don't cancel. If they don't cancel, what does that mean? It means very clearly that molecule of HOH cannot be linear. It has to be bent. And indeed, it is found to be bent. This is the argument based on dipole moment. But of course, please remember, this argument requires a prior knowledge, a prior experimental knowledge, if an overall molecule is polar or not. In this case, in this question, it was given. Right? Some data was given. Shape of H2O molecule and CO2 molecule was given to be bent and linear. Some data was there and we interpreted the data on the basis of dipole moment. This is how we did this. Write the significance or applications of dipole moment. What could be the significance? Well, significance number one. Dipole moment can be used to predict the nature of a given molecule, whether the molecule or the substance is polar or non-polar. If the molecule has zero dipole moment, then that substance is a non-polar substance, and if there is a significant dipole moment associated with every molecule, that means that substance is polar. A very good example is water is a polar molecule. Yeah, it has a significant dipole moment, so water is a polar solvent. On the other hand, if you have something like CO2 or benzene, they have zero dipole moment. That means they are non-polar in case they are used as solvents. That's the first point. Second point, well, you could actually use experimental values of dipole moment and make a reasonable guess about the molecular geometry. In initial days, this was quite useful because there were no advanced methods for actually locating the position of each nucleus. So, dipole moments have been very useful in actual determination of geometry of a given molecule. Third point, you could also determine percentage ionic character for a bond. No bond is purely covalent, no bond is purely ionic. Percentage ionic character of a given covalent bond can be very well determined in case you can measure dipole moment of that bond. So yes, these are the three major applications of dipole moments. What is electronegativity? Oh my God, and how does it differ from electron gain enthalpy? Electronegativity is very simple. What does it say? It simply says the tendency to attract a shared electron cloud towards itself. The tendency to attract a shared electron cloud towards itself. The tendency to attract the shared electron cloud towards itself in a covalent bond. In a covalent bond is said to be electronegativity of that atom. Electronegativity is defined for an atom. And how do we define it? The tendency of an atom to attract the shared electron cloud towards itself in a covalent bond is called its electronegativity. Atoms are not honest. Although they begin by sharing, but then they get greedy and they try to pull electron cloud towards themselves, away from the other one. The one which is able to pull it more effectively towards itself as compared to the other one, we say that atom, say for example in case B, in this case say for example molecule B gets this power. It can pull away electrons from A slightly, very slightly. So B acquires a very slightly negative charge, A acquires a very slightly positive charge. Why? Because B has gained electrons, that gets negative, A has lost electrons, it gets positive. And this tendency of B to attract more electrons as compared to A is called electronegativity of B as compared to A. Yeah, with reference to A. Does it differ from electron gain enthalpy? Very much. What is electron gain enthalpy? Electron gain enthalpy involves complete transfer of an electron. The tendency of an isolated gaseous atom. The tendency of an isolated gaseous atom to accept an electron to form isolated gaseous ion. That is called electron gain enthalpy, right? Or electron affinity in some cases. So electron affinity involves a complete transfer of electron, while electronegativity is simply just pulling away a small tug, a small pull of shared electron cloud. There is no complete transfer involved in electronegativity, while complete electron transfer is involved in electron affinity. First point. Second point, electron affinity is measured only in gas phase. Electron affinity is measured only in gas phase, while electronegativity can be measured in any phase. There is no restriction of gas phase or liquid phase or solid phase. As long as you have a covalent bond, you can talk about electronegativity. That's very simple, right? And then we have, explain with the help of suitable example a polar covalent bond. How sweet. We understand what is a covalent bond. A covalent bond is formed by sharing of electrons between two or more atoms, usually two atoms. So say if you have H and you have F. Let us take an example of HF. Fluorine atom has 7 valence electrons, while hydrogen atom has only 1 valence electron. Fine. They decide that we will share it. Lovely, share it. But the story does not end here. Actually, there's a problem. What? Fluorine gets greedy. Initially, might have been that, it was 50-50 sharing. Fine, we'll put electrons, we'll share electrons, we'll put them in between so that I can also enjoy electron presence and you can also enjoy electron presence. Great. But then the moment sharing happens, fluorine says, nah, I'm a gunda, I'm going to take more electrons. So as fluorine withdraws electrons towards itself, please note, the moment electrons are being lost by hydrogen and gained by fluorine, there is some negativity also associated with that. If you loot somebody, you get negative, right? So fluorine is also acting as a robber. So it will acquire a slightly negative charge, while poor hydrogen will acquire a slightly positive charge. And the moment there is a charge distribution, there's a slight positive, there's a slight negative somewhere, we say, oh my God, there are poles. There is one pole positive, there is a negative pole. So the molecule is now polar. It doesn't mean North Pole or South Pole of Earth, no. It's no polar bears involved. It is simply a polar molecule, and that's it. So, what is the polar covalent bond? Whenever two atoms having different electronegativities are joined through a covalent bond, always the atom having higher electronegativity pulls the electron cloud towards itself, thereby acquiring slightly negative charge, while the other atom acquires slightly positive charge. This makes the covalent bond a polar covalent bond. That's it. And not just that, the bond also acquires something which you call as a dipole moment. So the bond becomes a polar covalent bond, and it becomes associated with something which we also call as a dipole moment. But we need not mention it because in this question, nothing has been talked about the properties of a polar covalent bond. This much is sufficient. Done.